Okay, so let's start. So I said that what we'll do is this is an important topic, and the homework number 12 had lots of problems, and very few could be done in the tutorial. And so we'll go over it. So let's start with some of the basics. All the problems that you that are there here, they're all based on all BJTs have identical characteristics, NP, 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 simplified characteristics. So everywhere we take VB on 0.7, beta 100, early voltage 100, and C pi and C mu are given here. All right, these are some of the useful results. We need to remember these, that when I look from the base, these are all small signal results. When I look from the base, what I see is R pi plus beta times Re. These are simplified results. When I look at a transistor with a source attached here and a resistance attached in the emitter, when I look at it from the collector side, it appears as a current source, dependent current source with the value Gm times Vs divided by 1 plus GmRe, and a resistor looking from here, which is R0 1 plus Gm Re parallel R pi. So this is how this whole circuit appears to be. The other one that we know is if I have a transistor with the base and collector shorted together under small signal condition, it appears as a resistor. It acts as a resistor with the value 1 over Gm. And another one of them, that when I have a source attached to the base here, and when I look at it, this one was when I look at it from the collector. This is when I look at it from the emitter. And when I look at it from the emitter, it appears as a current source, and with a resistor with the value Rs plus Rb, R pi plus Rb divided by beta here. So these results are reasonable if these resistors that you see here, Rc and Rb, are much smaller than R0. If they become comparable with R0, then we have more accurate expressions for all of these. But in this particular course, we are not going to encounter such cases here. All right, so these are useful results to remember. The other one to remember is we'll again and again see a result for common emitter amplifier, that a common emitter amplifier where we apply a voltage at the base and take output at the collector. The gain of this particular one, V0 by Vi, is Gm Rc parallel R0. And similarly for the PNP. By the way, all the results that I've shown here, they're all valid if you just take the NPN out and replace it by PNP. Exactly same results. Nothing changes because the small signal model of NPN and PNP are the same. Okay, so all the results are identical for PNP as well. So here also, you apply at the base, take output at the collector, V0 by Vi minus Gm R0 parallel Rc. And as I was telling, that one can in general, for a common emitter amplifier, you may not always have an RC, you may not always have this node connected to ground. In general, if you're building a gain at this particular point, the gain will be Gm. Whatever is the resistance on the upper side, R up, and whatever is the resistance on the lower side, R down. All right. So that's a more general expression. And we've been telling that, whenever you have to build a gain at any particular point, or you want to know the voltage at any particular point, what you do is you build a Norton's equivalent at that point. At that particular point, you build a Norton's equivalent. So when we build a Norton's equivalent at this particular point here, what would happen is you'll get a Norton's current. And how do you find Norton's current? Well, you take this node and ground it. And Norton's current, then when you take this node and ground it, this one is nothing but Gm times Vi. So that's the Norton's current. And what is the Norton's resistance? When you look from here, when you look at any particular node, there may be a part of the circuit on the upper half, there may be a part of the circuit which is lower half. So that's what we are saying, upper half, whatever is the resistance, lower half, whatever is the resistance, parallel combination. Okay? So whenever you encounter a new situation and you have to find a gain or a voltage at that particular point, small signal gain, a simple method would be build a Norton's equivalent. Okay? All right. As an example, this is what we had seen in the lecture also. So if we want to find the gain, let's say V0 here at this particular point. Now the first thing is to recognize that does it fall into any of those blocks that I already know. So when I look at here, when I apply at the base, and I'm asking voltage at the collector. And note that all this lower half, there is no source applied here. So the lower half is all, if you see a block of circuit and you see that there is no source anywhere applied, independent source, under small signal condition is all a resistor. The whole thing is a resistor. Okay, so this is nothing but a common emitter amplifier with a PNP transistor here, with a voltage applied at the base, and all this is acting as a load here. All this is acting as a load. So as we said, the gain of this amplifier will be GM4, because this is where I'm applying the input. So GM4 multiplied by, at this particular point, at this particular node, we say what is the resistance looking up, R up, and what is the resistance looking down, R down here. So when I look up, remember I'm looking at the collector, and collector, when I look up into the collector, we said is the resistance, is the output resistance of the transistor, R04. And when I look down, I'm again looking down into the collector of Q2, and the resistance is R02, 1 plus GM2, R05. Sorry, it shouldn't be R05. Okay, R05, fine, parallel R pi 2, right? And the other thing is, we've been saying make approximations as early as possible. Don't take an expression and start making it more and more complex by adding more and more things here. So instead of taking the whole thing and then doing an R parallel with this, then writing down a big expression, don't do that. Simplify it right here. So when you see here R05 parallel R pi 2, remember R0 is much larger than R pi, and R pi is much larger than 1 over Gm. These three resistors you'll encounter again and again. R0, R pi, and 1 over Gm. And you should know R0 is much larger than R pi, and R pi is also much larger than 1 over Gm. So use that to simplify. So we'll throw R05 out. Gm2 R pi 2 becomes beta, and we'll throw 1 out also. We will not keep 1 in relation to beta. So this becomes beta R02. So it is beta R02 parallel R04, and we know that this is simply going to be GM4 R04. Okay? All right. So these were some of the useful results. Another set of useful results, because we are discussing differential pair. So let's look at a differential pair, a little bit of revision here. So differential pairs are, one part of the analysis, of course, is a bias point. Bias point analysis, because in differential pairs, we don't say DC and AC and small signal. In differential pair, because note that the input can also be a DC. Okay? So in differential pairs, we specifically make a distinction that what we are doing is, we are doing a bias point analysis where we remove the sources in the sense that we make it ground. That's bias point analysis. And then we do small signal. The small signal can be DC, AC, whatever it is. Okay, so so don't say DC analysis and AC analysis. That's not correct here. And so bias point analysis is usually straightforward. You know, when you put it to 0 here, this point becomes minus 0.7, and then you determine whatever is the current. Keep in mind that the two transistors are, most of the time, in most of the problems, we'll say Q1 and Q2. If nothing is said, assume that Q1 and Q2 are matched. Okay, problem may not say it explicitly, that Q1 and Q2 are matched, but if nothing is said, they are matched. Okay, they have identical characteristics. So whatever current is here, of course, divides between Q1 and Q2, and that's fine. So bias point analysis is straightforward. Small signal, we break it down always into two parts. We break small signal into a differential part and a common mode part. So the first thing to do is take V in 1, whatever V in 2 is given, calculate what is the differential part, what is the common mode part. Okay, VID and VIC. And then, so the input that you see here can be written in terms of differential part here and a common mode part here. And we said that we can break the analysis into two parts, differential mode and common mode. So eventually you would like to find what is V01 due to V in 1 and V in 2, but you do that in two steps. You find out what is V01 due to VIC, the common mode signal here. And you find out what is V01 due to the differential mode signal here. And then you add them up, because these are linear circuits. And we are doing small signal linear circuits, so we can use superposition. And so you add the results V01 due to here and V01 due to here. So we always break the analysis into two parts, differential and common mode. All right, when you and at any point, you know, if you take at any point in the circuit, whether it's a voltage or a current, It's made up of two parts, the quiescent point or the bias point and the small signal point. And the small signal, we said, is made up of a differential part and a common mode part. All right, so three analyses you have to do: bias point, differential mode, and common mode here. All right, so similarly, for example, if somebody asks you, what is the net value of voltage here? Net value, total. So total value would be the bias point plus the differential part contribution to it and the common mode part. Okay. Similarly, if I ask what is the current flowing through Q1, collector current of Q1, the collector current of Q1 will have a bias point, a differential part, and a common mode part. Everything will have, in general, these three components here. Okay. And the differential part you find out through the differential mode circuit. The common mode part you find out through the common mode circuit. Okay. So these are the three things here. Differential part. When you do differential part, you have plus a voltage here, minus voltage here. And what we said was when you do differential part, because of the symmetry, you assume it to be ground here, small signal ground, and the circuit separates out into two parts here. So whatever lies below this emitter in differential part doesn't contribute anything because this point becomes ground here. All right. And then the circuit simplifies and you calculate whatever is the gain at this particular point. It's a simple common emitter amplifier. So it becomes GMRC minus GMRC 0.5 VID. Similarly here, minus 0.5 GMRC minus 0.5 VID. These are things that we have seen earlier, and you can calculate differential mode gain and RID and all that from a circuit of this kind. Now, one point that I would like to emphasize is this is a perfectly symmetrical circuit. Perfectly symmetrical, transistors are the same, RCs are the same, and obviously you can see that I can put ground. So in this case, it's obviously valid. But there can be situations here, let's say when RC1, I have RC1 here and RC2 here. Say 2K here and 4K here, or whatever. The resistors are not the same. Now, you may think, can I apply, can I make it ground? The answer is strictly no, but practically yes. Okay? Strictly speaking, is no longer fully symmetrical, and therefore this will not be. But what happens is, note that if RC and RC here are different, what are the consequences of it? The voltage here and the voltage here are going to be different. The bias points are also going to be different, right? The same current, the bias point here and the bias point here are also going to be different. But note, because of differences in the collector, voltage here, whatever is the voltage here, whatever is the voltage here, it doesn't have too much impact on the current, because how does the collector voltage affect the current? Through the early voltage. And if the early voltage is large, and these voltages are not so large here, then what happens is, even though the voltages here and the voltages here are different, it doesn't have too much of an impact, because the collector voltage does not have a significant impact on the current flowing through the transistor once the transistor is in forward active mode. Okay, so even in this case, if RC1 is different from RC2, it's a fairly good assumption that you make it equal to ground. Okay, so in differential mode, you make this equal to small signal ground, and the results are going to be fairly accurate. Even to the extreme, let's say I have an RC here and I don't put any RC here. I take this node and I put it to directly to ground. I don't even have an RC here. Even then you'll find that this point is reasonably small signal ground. Okay, so you can make those assumptions. And we saw in, yes. So as I said, if you have RC1 and RC2 here, again it separates out. It separates out because we are putting ground, right? So there'll be left half of the circuit with RC1, and you'll have a right half circuit with RC2. And then each one of them is a common emitter amplifier. So in a I cannot make a general statement that yes, it's valid in all possible cases. But what I'm saying is, especially when you have a resistive load here, the voltages may be different, and even in these cases, you can apply and assume it to be small signal ground. All right. I could put something here, maybe a transistor or something else. There could be some situations where maybe this is not a very good small signal ground. But in most of the practical cases, that's what I'm trying to tell you, is if you're looking at it from all the problems that we have encountered and all the problems that you are going to encounter, yes, in differential mode, you can go ahead and put it. But remember, Q1 and Q2 have to be matched. Q1 and Q2 have to be matched. So all that I'm saying is above this particular point, you could put RC1, you could put RC2, and still, because the collector voltage does not have a big impact on the current flowing through Q1 and Q2, I don't have to bother too much about these parts here. I would still have a reasonable small signal ground here. Yes. Where current source? In place RE, yeah. Yes. That's what I'm saying. It doesn't matter what is below this particular point. I have a transistor, I have 2 transistors, 3 transistors, whatever you have. Note that this point we are writing because Q1 and Q2 are matched. And the voltage that I apply to the base is positive, whatever, it has some value. And the voltage that I apply to the base is exactly the same magnitude and negative. Is these two things here, this and this are equal and opposite, and Q1 and Q2 are matched, which causes this node to become ground. Not so much as that this voltage has to be exactly same as this. If it is there, that's a perfect condition. But even if these two voltages are not exactly same, you can still make this node would be reasonable small signal ground. Okay? And so in differential mode, note that differential amplifier will separate out in 2 halves. But matching is very important. Do not forget, there will be problems where, for example, we'll encounter just now, where we have said Q1 is, the saturation current of Q1 and Q2 are different. And if there is no matching, then there is a problem. Okay? Common mode, on the other hand, so in common mode, the signals on both sides are the same. And what happens is that whatever is below here, it gets duplicated. If I have REE, it becomes 2 REE and appears on the left-hand side, and 2 REE appears on the right-hand side. Because he said we can break this into 2 parallel resistors here, and then break the connection in between. So here also the circuits separate out, a left half and the right half. Okay? And the left half becomes here, right half is exactly the same, and then you have to calculate here. So differential pairs, if you look at it, what happens is after you do differential or common mode, they actually reduce to a common mode, a common emitter amplifier. Common emitter amplifier, why? Because you're applying input at the base and taking output at the collector. So they all become a common emitter amplifier. That's why common emitter amplifier results are very important. Okay? So ACM, then you can calculate V01, VVIC. We know how to do that. And resistance and all that we can also calculate. All right. So this was our mini quiz problem. So this must have been discussed. RID. So these are straightforward application of formulas. ADM, RID, ACM, minus GM 1 plus 2 GM RE RC. This was our general expression for ACM when there was a resistor here. And when you have an ideal current source, it's written here, assume ideal current source. So in ideal current source, the small signal resistance of ideal current source is infinity. RE is infinity. So ACM goes to 0, RIC goes to infinity. So whenever you bias a differential pair with an ideal current source, your common mode gain will always be 0. Common mode gain will always be 0, RIC will always be infinity, which means that the only analysis that you have to do is differential mode. There's no common mode. So I could have had here, let's say the same problem was there. Suppose I had put here 1 volt here and 1 volt here. Or 0.5 volt sine omega t, 0.5 volt sine omega t. It will have no impact on V01 and V02. Common mode gain is 0 here. All right. So with an ideal current source, common mode gain is 0 and RIC is infinity. All right. So several places you'll find that we'll bias it through an ideal current source just to make things more simpler here. All right. So let's start with problem number 1. We have, I think, 11 problems, so I'm going to go over them quickly. After this, it would be best that if you sit down and I'll post the solutions, don't look at them and try to solve them yourself. Okay. All right. So here, so it's a straightforward differential pair. We are given VS1, we are given VS2, we are given all the values here. So all that you have to do is, this is just learning the basic things here, calculating IEE. The first part is bias point analysis. So you calculate IEE here, taking minus 0.7 here, and remove all the small signal sources here. and calculate the IE here. You know ICQ1 here. Calculate the bias points here. After you do the bias point calculations, calculate all the gains, ADM, 0.5 minus 0.5 GMRC, ACM minus GMRC 1 plus 2 GMRE. These are fundamental equations for a differential pair. You should remember them rather than drawing a small signal in the exam and trying to find out what is now differential mode gain and what is common mode gain. Although the derivations are also basically two-step derivation. These are not hard. Anyway, so we know ADM, we know ACM. The next thing is, as we said, we are asking what is the net voltage? Net voltage including DC and small signal components at here and here. So net voltage would be bias point plus a differential mode plus a common mode. So all that we do is bias point we've already calculated. Differential mode would be differential mode gain multiplied by the net differential signal. The net differential signal would be whatever is connected here and whatever is connected here, the difference of the two. So when you take the difference of the two, it comes out to be 2Vs1. And common mode part would be the common mode gain multiplied by whatever is the common mode signal here. So whatever is the signal here, you take the average. So the average is Vs2. So that's how we find out what is V01. And V02 would be same bias point, differential part, and common mode part here. Note that the differential part here is plus ADM and here is minus ADM. So in differential part, please keep in mind whatever is the voltage developed here, the voltage developed here would be minus of that. Note that this is important point here. In common mode, whatever is the voltage developed here, the same is the voltage here. So this remains ACM, remains the same here. Note minus 0.53, minus 0.53 here. The differential part, this is minus, this is plus. And then the bias point here. Okay. So these are the basics of differential pair. What is the simplest differential pair that we can talk about? What is differential mode gain? What is common mode gain? We could have asked, what is RID? For example, I could have asked, what is the net current flowing in the base of Q1? Net current flowing into the base of Q1. Suppose I ask that. So the net current flowing in the base of Q1, if we write IB, would be equal to the quiescent base current, the differential mode base current, and the common mode base current. Now, the quiescent base current would be whatever we've already calculated collector current divided by beta. Fine. The differential mode base current. The differential mode base current would be whatever is it. Now you look at the differential mode circuit. In the differential mode circuit, what do I have? Note that we have Vs1 here and minus Vs1 here. And you know, when I look from here, this point is ground. So basically it is R pi, right? Between here and here is R pi. So it would be Vs1 by R pi. So you calculate what is the differential mode current here. And similarly, you know what is the common mode circuit there. And you calculate what is the common mode current. Okay. So as I said, everything is now two parts here. So you should know what is the differential mode circuit, where this becomes ground. What is the common mode circuit, where this becomes 2RE. And on that basis, then you can calculate what is the base current here and what is the base current at this particular point, net value of base current. All right. So similarly, suppose I say what is the net value of current flowing through this particular point, through this resistor. Net value of current flowing through this particular resistor. It would have a bias current, right? Will there be a differential current here? Because we said in differential point, this point is 0 and this point is also 0. So there is no differential current here due to differential signal. Will there be a common mode current? It will be there. All right. So you'll have to calculate that. All right. So I'm just saying same thing you have to repeat for whatever quantity that you're asked. All right. Let's come to this one. All right. So note. In this particular problem, we are given a voltage on this side, we are given a voltage on this side, and we are given a current source. And it's written that current source is ideal. So the moment current source is ideal, the first thing that comes to your mind is common mode gain is 0. Common mode gain is 0, so I only have to bother about differential mode gain here. Okay. So anyway, we are asking, determine the DC value of collector current. Note, DC value of collector current. At this point, please do not get confused that if I say DC value of collector current, do not think that we are asking for bias current. Don't think that I'm asking for bias current, and therefore what you should do is make this ground and make this ground and just get the value of bias current. DC value of collector current does not mean bias current. Okay, because we said in a differential mode amplifier, the input could also be a DC. All right, so bias. So when I say DC value of collector current, we recognize that both these voltages that I've applied to the inputs are also DC. Okay, so now the DC value of collector current here will have what? A bias value plus a differential mode value plus a common mode value. All right, because there's a signal attached here. These are signals for us. Okay, so we'll have a differential mode, we'll have a common mode. Now we know that common mode gain is 0. In common mode, because we have an ideal current source, so all common mode quantities will be 0. So I don't have to bother about common mode here. So let's see, let's go forward. So IC would be bias or quiescent point, differential mode part, and common mode part here. ICM it should be. Common mode gain is 0. I don't have to bother about it. Though there's a common mode signal here. Common mode is whatever is average of these two is about 1 volt. Differential mode is 0.005. Okay, differential mode is 0.005 here. Because VID is small signal analysis can be applied. There can be situations, remember that there can be situations here where what if I had applied here 2 volt and applied here 1 volt. Suppose I'd applied here 2 volt, which we will encounter later on. I had applied here 2 volt and I'd applied here 1 volt. Then, well, I have this thing, so common mode I don't have to bother. Differential mode signal would have been 1 volt. And when you have a 1 volt differential mode signal, I can't do a small signal analysis. Because remember, when you apply, we had discussed this long back, when you apply voltage at the base, small voltage at the base, to be considered as small signal, the effective base emitter voltage, small signal voltage, base emitter voltage, has to be much smaller than the thermal voltage. Small signal base emitter voltage has to be much smaller than the thermal voltage, your VT. So we are talking about signals which are, a VT is 26 millivolt, we are talking about signals which are significantly smaller than VT. 2 volt, 2 millivolt, 5 millivolt, maybe 10 millivolt. The moment we go to 15 and 20 millivolt, we are stretching it. Our analysis will become more and more inaccurate. But here, if I say 2 volt here and 1 volt here, obviously small signal analysis is out. I can't write it in this form, that there's a differential small signal analysis and there's a common mode. So small signal analysis is out, and we'll see how to handle those cases here. Anyway, so IC1, because note that 1 milliampere will divide into 2, 0.5 and 0.5 here. So 0.5 milliamperes is the bias point, and I have only the differential part here. And in differential part, please recall, this point will become ground. Okay, and what is the differential signal that appears here? VID by 2. Note, what is the net VID? 0.005, 5 millivolt. The differential part that I put here is VID by 2 here, and the differential part that I put here is minus VID by 2 here. Okay, so the effective signal at the base is VID by 2. And we are asking how much is the collector current. Now note that if I have a signal base emitter, this is ground, if I have a base emitter voltage, which is VBE, how much collector current flows here? GM times that. Okay, so that's where it is, GM VID by 2. And on this side, note, I have minus VID by 2 here. So the collector current that will flow is minus GM VID by 2. Now, you may be wondering, when I look at it from the collector side, there is also an R0. So in these circuits, we do not bother. If nothing is given here, the current that flows through the R0 part is very small, very much smaller than this part here. So we neglect it. Okay. So that's how I find out the next net value of collector current here and the net value of collector current here. Note that this value would be a little larger than 0.5 milliamperes. This value would be a little smaller than 0.5 milliamperes. Okay. Now we come to an interesting part. We have been talking about all the transistors are matched. There can be situations where the transistors are not matched. Okay. So in the differential pair, there's a mismatch between transistors Q1 and Q2. And we are saying the saturation current of Q1 is 1.5 times the saturation current of Q2. Determine collector currents of transistor Q1 and Q2. So there is no signal as such applied. Both sides are ground. All right. Both sides are ground. Now, we had said that 1 milliampere will divide equally between these two if they're matched. If they're exactly the same, they're no longer matched. Then in this situation, what do we do? Well, in this case, what we have to go back and realize that the collector current of a transistor is equal to, we had seen that long back, saturation current times exponent VB by VT. And if you recall, there was another term, 1 plus VCE by VA. And we are saying that VA is very large, and therefore we are not bothering about that particular part. Okay, but this part obviously we cannot neglect. So this is a more IC equal to IS exponent VB by VT. This is the basis of when we say the two transistors are matched, what are we saying? IS is the same for both of them. And note that if the two transistors are matched, their base voltages are the same, and emitter is obviously common. And therefore, on that basis, we say IC of this transistor is same as IC of this transistor. But now that IS is different, what we need to do is, we have to write IC1 is IS1 exponent VB1 by VT. IC2 is IS2 exponent VB2 by VT. In general, let's take the ratio IC1 by IC2. Note that base emitter voltage of 1 and base emitter voltage of 2 are exactly the same. They cancel out. So IC1 by IC2 is 1.5. And the sum of the two we already know is 1 milliampere. And therefore we find out whatever is the value here, 0.4 and 0.6. Okay. So in this case, when there is a mismatch, then this is what we have to do. Or this is the general way of doing. If I had a voltage here, voltage here, and I couldn't handle it through small signal analysis, we have to go back to these fundamental equations. Okay. If you can't do small signal analysis, go back to this basic equation. IC equal to IS exponent VB by VT. That's how the collector current goes here. So depending on the input here and the input here, you could write whatever is the collector current in this branch, whatever is the collector current in this branch. Okay. All right. The next thing is, fine, we have a situation like this. Q1 and Q2 are, there's a mismatch between Q1 and Q2. And so we calculate how much current is flowing here and how much current is flowing here. Then we are asking in the next problem, determine the extra voltage Vin that needs to be applied to transistor Q1 here in order to make the collector currents of both the transistors identical. Okay, where is the collector current higher? IC1 is higher than IC2. This is 0.6 and this is 0.4. So 0.6 is flowing here and 0.4 is flowing here. That's what you find out. Now we are saying, let's attach a small voltage here. How much voltage do I have to attach here such that these currents here and here become the same? Okay, well, we do the same thing. IC1 by IC2 is exponent IS1 by IS2 exponent VB1 by VT, this one here. And we say now the currents are the same. So we make it equal to 1. All right. And note that now if I start from here and start from here, Vin, write a Kirchhoff's voltage law, come here, go here and come to ground here. All right. Start from here, from this ground, go here, 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 and come back to ground. You can easily see Vin equal to VB1 minus VB2. The applied voltages, Vin is VB1 minus VB2. This doesn't matter. It's a current source here. So Vin, now you can see here, when you take the ratio, you'll get VB1 minus VB2. So from here, you can calculate what is the value of Vin that you have to apply, 10.54 millivolt. So these situations where there's a mismatch and all that, then we, as I said, if through normal small signal route we cannot handle it, then go back to this fundamental equation. IC is IS exponent VB by VT. Try to attack the problem by this equation. Okay. All right. Question number 4, where we have the usual differential pair, except that as you can see here, we have replaced the transistor by a Darlington pair. Darlington pair here and Darlington pair here, and we are asking what is the differential mode gain and input resistance for the amplifier shown in this particular figure here. So differential mode circuit is First thing, note that the collector current of IC2, first of all, can we calculate what is the collector current of Q2? Yes. Shouldn't be? You are right. V in 1, IC1 is larger 0.6 as compared to this. So I have to apply a negative voltage here. Yes, it must be minus here. You're right. This should be minus 10.5. Correct. All right. So coming back to this, what is the collector current of, note that is symmetrical. All right. How do I calculate Q2, collector current of Q2 and Q4? This point would be 0. When I do bias point analysis, remove VS1, VS2, put it to 0 here, 0 here. This point would be minus 0.7. This point would be minus 1.4. And this is minus 12. So you can calculate what is the current here. And once you know the current here, you know the current in Q2, you know the current in this one here. Fine. In both of these you can calculate. And once you know the current here, then beta divided by beta is the current flowing in this particular transistor. And divided by beta is the current flowing in this particular transistor. So that's how you do the bias points. All right. Once you do the bias point, so we know the relationship IC2 is beta times all of that here. You can find out what is GM2, RPi2, all of those things you can find out. Okay. And you can also note the relationship between RPi2, RPi1, all of that. So we have handled Darlington pairs earlier. And this is, so in differential mode, what would happen is effectively my circuit, as I said, this point will become ground. And we'll put here 0.5 VID here. And so effectively, this is the circuit that I get here. And what we need to analyze is what is the gain and what is the input resistance of this. So we have done this before, but let's quickly go over it here. If you want to find out what is the gain at this particular point, one way, as we said, is build the Norton's equivalent at this point here. Which means you want gain here, the whole circuit here, convert it into Norton's, IN and RN. So break it down into two parts. Ask yourself, what is the net Norton's current at this particular point? What is the net Norton's resistance at this point? Norton's resistance is, and then the voltage gain would be, note that V0 would be simply minus IN RN divided by VS. Whatever is the input applied here. In this case, the input applied is 0.5 VID. So we'll put 0.5 VID here. So anyway, so we have to calculate what is IN and RN. RN is straightforward. When you look at this particular node and you ask yourself, what is the resistance looking down? What is the resistance looking up? When you look up, you see RC. When you look down, you are looking into the collector of two transistors. And when you look into the collector, we said resistors are at least R0. And if it's at least R0, we've always been neglecting R0 compared to RC. Okay? So we just put Rn equal to RC. So Norton's resistance is straightforward. What we have to do is calculate Norton's current. So Norton's current means that particular node you connect to ground. You connect to ground and you ask yourself, what is the current flowing? All right. So when we look at it, we can make an approximation. Although this node is ground, and IN is made up of whatever current flows through Q1 and whatever current flows through Q2. It's the sum of these two currents. But you can make an approximation because the collector current of Q1 is actually beta times smaller than the collector current of Q2. So I can neglect that. IN is made up of these two currents here. This current is much smaller than this. So we take it out, we put it to ground, and we say IN is primarily this. Okay. Now this part, any of these circuits can be done in many different ways. Okay. I'm just pointing out one way. So when you look at this particular part here, all right, so we've already said this. When I look from the emitter side, this part appears as, the whole thing appears as a current source 0.5 GM1 VID, a current here. And when I look at from the emitter, the resistance that I see is, we know, 1 over GM1. Okay. So that's one of the results. And then what you can see here, as I said, there are many ways of doing it. So what you can see here is now this current has two paths to flow through 1 over GM1 or flow through RPi2. So there is a current division. There's a current division, And that's what we are writing about this current division here. The fraction of current which flows into the base of this transistor would be 1 over GM1, 1 over GM1 plus R pi 2, because the resistance of this one is R pi 2. And this is the current here, 0.5 GM1 VID. So this current, the fraction of current which flows into the base of this transistor is this one here. Okay, this is the current division part here, this is the current here. Now whatever current flows into the base, we know that current gets multiplied by beta, and that would be IN. Okay, so that's how we calculated IN. As I said, there are other ways in which you can do it. Whatever way you do is fine here. All right. So this is 0.25 GM2 VID here, and then after that is straightforward. ADM is minus IN RN by VID, so we get the value, which is 1/4. So when you put a Darlington pair here, the normal value was, if you recall, GM2 RC 0.5. When you put Darlington, what happens is the voltage that you apply here, half the voltage gets dropped here and another half drops here. The voltage gets divided. This voltage that you see here, only 1/2 appears across Q2. And only 1/2 which appears across Q2 contributes to the current here. The other half does not contribute that much. Okay. Input resistance is also now straightforward. When I look from here, we know this part is simply R pi 2. And then when you look from the base, it will be R pi 2, 1 plus beta plus R pi 1. And after looking at the relationship between R pi 1 and R pi 2, one can write it as 2 beta times R pi 2. So it becomes 4 beta times R pi 2. All right. So these are, I'm going over it fast. Please try it out yourself, this thing. So ADM RID by R0, we've been saying this, that this is a figure of merit for amplifiers. And because we've used these two transistors, comes out to be beta square. Unlike a simple differential pair, which would have been simply beta here. All right, let's look at this one. Question number 5. Okay, so in this case also, note that what we are saying is 2Q1, a regular differential pair. We've added a capacitor here. And what we are saying is we are applying a step input of 1 volt. A step input of 1 volt. And this is 0 here. So the first thing to realize is the moment I apply a step input of 1 volt, the voltage here becomes 1. The voltage here is 0. VID becomes 1 volt. And when VID becomes 1 volt, small signal analysis is out. I can't do that. Okay. So we have to handle it in a different way here. All right. But before you calculate what happens after I apply V in, you have to put this node to ground, calculate what are the bias voltages here. So the bias voltages are straightforward, 1 milliampere, half flows here, half flows here. The drop here is 6 volt, the drop here is 6 volt. So the bias voltage here is 6. Before I apply the input, the voltage here is 6 volt. And therefore, is 6 volts, so the capacitor would be all charged to 6 volts. Right? 6 volt. Now what is happening is I apply a step of 1 volt. I apply a step of 1 volt here. Now what would happen? 1 volt step. Remember we said, how do you handle this? You handle this by saying the collector current here is IS1, VBE1 is exponential of VBE1 times VT. The collector current of this one is IS2 exponent VBE2 by VT. Okay? VBE1 by VT and VBE2. These are exponentials. Now what do you think is the difference between the base emitter voltage of this and base emitter voltage of this? 1 volt, right? And 1 volt. And where does this 1 volt go? In the exponential. So what can you say about IC1 versus IC2? I mean, 1 volt, right? Remember, 1 volt by VT. VT is 26 millivolts. So practically, what would be a very good assessment of how much current flows here and how much current flows here? The whole current that you see here, 1 milliampere, will flow through Q1. The whole current will flow through Q1. Nothing will flow through Q2. Which means what? If nothing flows through Q2, Q2 is cut off. No current flowing through Q2. So this whole thing goes away. So can you see now what would happen is on this side, I'm interested in what happens to the voltage here. On this side, the circuit will become 12 and 100 pf. Nothing is flowing through Q2. Nothing is flowing through Q2. Through Q1, I will have 1 milliampere flowing. So the whole circuit reduces to 12K and 100 pf. Now what would happen? What was the starting value of this capacitor here? 6 volt. Now what will happen to this capacitor? It's connected 100 pf, connected 12K to 12 volt. So this capacitor will charge and will go up to 12 volt. So that's what will happen. The 6 volt to eventually 2 volt here. And I'm asking determine the time taken for output voltage to reach 10 volts. All right, so it's a simple RC charging. We can write here VCT is 12 minus 6 exponent minus T. The time constant would be collector resistance times this one here. And then you should recall your ESC 201 for RC charging. What do you write? How do you write VC here? VC infinity, the value that it goes to infinity, plus V0 minus V infinity e to the power minus T by tau. All right, and tau is RC here. Okay, so this is what you write, and we are asking how much time does it take to reach 10 volts. So you put 10 volt here, and then you calculate. Okay. So when you don't have the small signal input voltages here, you have to look at it from the basic transistor equation, which is collector current is Is exponent VB by VT. Okay. All right. Look at this one. Okay, so this is straightforward. It's straightforward application of formula. ADM, RID. All we have to do is determine the value of RC and RE such that the differential input resistance is 52K, differential mode gain is 100. All you have to do is just put in the values here. Differential is resistance is given 52K. You put here 52K. That will give you the value of R pi. That will give you how much collector current I'll get in Q1 and Q2. So how much current I require here. And from there you'll see how much RE do I require here. ADM. So RID will give you the collector current. And once you know the collector current, you know GM. And ADM will give you then the value of RC. Right? So straightforward application of these two expressions here, ADM and RID. All right, so this is interesting. So we have a differential pair. See, if you think about it, when we make problems, what are we going to do? We have this basic differential pair. Either there is a resistor connected here or there's a current source here. So when I'm going to make a problem, what am I going to do? I'm going to create variations, right? This is what you do. I mean, if you want to take a circuit and you want to improve it, what do? You create variations. We said you ask, what if I do this? What if I do that? So that's what I'm going to do as when I make problems for quiz or for NSEM also. I'm going to take these 2-3 basic differential pairs and I'm going to create variations. All right. One of the variations that I said was, okay, so far we've been making this ground and make this ground. Let me just put an R here. What if I put an R here? What will happen? Okay. So that's what this particular problem is. And in fact, you can generate your own questions if you want to practice. You can take this basic circuit and create variations. You can say, what if I remove this? Or what if I add something here? Or what if I add here? And see whether you can analyze them. Create variations in the circuit and see whether you can, with paper and pen, you can work out what are the implications of those variations. All right. So you can make lots of problems yourself and analyze them. And after you do that, then that will give you practice here. Anyway, so this is slightly done in a different way. I could have asked this problem by simply saying, suppose I have 0 here. I don't apply any voltage here. And so this is ground. And this is here. And if I put an R, what are the implications of putting an R here? I've done it in slightly other ways by saying that with the input not being there, we said one of the voltages is 5.5 and the other voltage is 6.5. Which makes sense because when you put input to 0 here, the circuit is no longer symmetrical. The circuit is no longer symmetrical. There's something connected here and there's nothing connected here. So the circuit is not symmetrical, and there's no reason to expect now that the 2 milliamperes will divide equally between these two. Okay, that equally between these two, and that's why the voltages are different, 5.5 and 6.5 here. So the issue is now, which one is this 5.5 or is this 6.5? All right, so that's what we have to figure out. So we have to look at the implications of R. So what we see is, so this is what we are looking at without V in. So what we are looking at is, if I look at this particular circuit here, there is the Q1 and Q2 are biased. The currents are going to flow through Q1 and Q2. So there is going to be a base current flowing here, and base current means that there's going to be a voltage at this particular node here, minus IB1R at this point here. Note how the base current starts from here, flows here into it. Okay, so this node would be a little bit negative. Minus IB1R is a little bit negative as compared to this particular node. That's the implication of R when you put R here. This node is negative compared to this. And now we know the expression of IC1 and we know the expression of IC2. If the base voltage of this is a little bit negative compared to this, we know that IC1 will be less than IC2. IC1 will be less than IC2 because the base voltage is negative here, base voltage is 0 here. So IC1 is less than IC2, which means that the drop here is less as compared to this, which means this must be 6.5. This is where I must be having 6.5 volt, and this is where I must be having 5.5 volt. All right. So that's how we figure out which one is 5.5 and which one is 6.5. We can also find out which one is how much, now that we know how much is the current that is flowing here and how much is the current that's flowing here. Okay. Now, do you think you can find out how much is this R? We have not asked that, but how much R do I have to put to get this situation? How much R do we have to put? It's easy, right? Because note that IC1 and IC2 you now know. So when you take the ratio of IC1 and IC2, what do you get? You get VBE1 minus VBE2. So you'll get that value. And then VBE1 minus VBE2. So from there, you'll figure out what is the drop here. Right? And what is the drop here? You know the collector current here, so you know the base current also here. And so once you figure out how much drop I need here, base current you know, so you can find out how much R do I have to put there. So how much R do I need to create a situation like this? Okay. Now, this is important because many times what happens is, you may apply, forget about this, I may have applied a signal from here, and the signal has some resistance with it, RS. Signal may have some, so I'm applying a signal here from this point, and the signal has some resistance with it. And so what we are saying is, apart from Vs, the signal resistance will cause a distortion, will cause once more current to flow here or less current to flow here. So if you want the differential pair to remain balanced, what you should do is, if you have a signal here and it has a certain R, what you should do is go ahead and put the same value of R here also. So the differential pair will remain balanced in the sense IC1 and IC2 will remain the same. All right. And then whatever is the signal here, then of course it goes through and gets amplified. The next part is, all right, so we know now how much is the voltage here and the current here. How do we balance it? How do we make the two currents the same here? All right. So determine the approximate value of small signal DC that I have to connect here. Small signal DC that needs to be applied to make both the collector voltages equal to 6 volt here. Okay, so one straight way of doing this is, as I said, you can find out how much is the drop here now. Because I know IC1, I know IC2, so you know how much is the how much negative this voltage is, VB1. You can calculate that, and the same value that you have to apply here from V2 side to balance both of them. Okay. All right, so let's leave it at that. I had a different way of doing it, but here. Let's come to this one. Question number 7. Determine the common mode gain of the differential amplifier shown below. All right, so common mode gain, what do we do? Note that this circuit looks, part of it looks familiar, part of it is not familiar. What is not familiar is whatever is down here. But we know an expression for common mode gain, which is this one here, where we had a resistor here. Now, everything is the same in this circuit. I only have to find out what resistance does it correspond to. And remember that resistance that is there is, in common mode, I have to find out what is the small signal resistance. What is the small signal resistance of this whole block here? That's it. Otherwise, it's exactly the same expression, GM, RC here, 1 plus 2 GM RE, everything is the same. All I have to find out is the small signal resistance here. That's all. Okay? And the same expression is valid here. Now, what is the small signal resistance of this block? When I want to find out what is the small signal, I have to look into the collector. I have to look into the collector. This is bias voltage. It becomes ground. This is Q4. And remember, this is nothing but 1 over GM4. And so the resistance becomes R03, 1 plus GM3 into 1 over GM4. Simplified form. The two transistors are in series. GM3 is same as GM4. So it's simply equal to 2R03. So all I have to do is ACM is minus GMRC, 1 plus 2 GM, 2R03. That's it. All right. So there's no need to go back and do all the analysis. Always, wherever possible, always try to take whatever is the unknown circuit, try to transform it into the known circuit. And this is the known result. So instead of doing, I'm again and again saying, don't do analysis from scratch, from first principles. Seems very attractive. Let me start from, first principle. We don't do that. None of the experts do that, let me tell you. None of the analog designers, none of the experts will say, given a circuit, let me just lay it out, big circuit here. None of them do it. Okay. Part of expertise is, as you become an expert, part of expertise is recognizing this is what it is. And let me use the results that I'm familiar with, the experience that I have. Okay. So that's what I'm saying. You already know that I have an RE here and I know the result of this. Okay. I know the result of this. Let me transform my unknown circuit, new circuit into the old circuit here. And if I can transform it, then use all the results that are there for the old circuit. Okay. So do the transformation is very, very important, very, very useful, not just here, but, everywhere else in engineering that you see here. All right. Okay. So this is now, as I said, I have to make 11 or 12 problems. I have to make 4 more quiz problems, a lot more answer problems. So I have to create variations, right? I have to sit down and create variations. So one of the variations that I said was, well, let's say my 12 volt supply has an AC ripple in it, right? And none of the supplies are perfectly ideal. If I have a ripple here, you know that I want perfect minus 12 volt, but I have a ripple here. Now this ripple, if I have here, this ripple is going to percolate and appear over here, right? And I want to know if there is an unwanted signal here, how much of it appears over here? A good amplifier would be such that even if I have a ripple here, very little appears at V0. That it sort of rejects any power supply variations here. It rejects it. Any ripple here is rejected and very little appears over here. Okay. So now note that I have a signal here, AC ripple. And the value of the AC ripple is given here. Magnitude is 1 millivolt. Signal is, the frequency is not given, so it's not important here. So I have an AC ripple, 1 millivolt ripple here. And I have to find out. Now, look at this. Is this signal, AC ripple, is it differential mode or is it common mode? Is it differential mode or common mode? Look at the two halves. Differential or common? Is it only present for one half, not present for the other half, left half, and not present for the right half? It's common. Now, one of the properties of differential pair is what? All the common mode part is usually rejected, is attenuated. So what would happen is this ripple is a common mode signal. And so what you'll find is as this ripple propagates here, its value will actually get attenuated. Okay, because it's common mode. Common mode signals are generally rejected. Differential mode signals are amplified here. All right. So this is a common mode signal here. So let's do that. So I'm assuming bias point analysis. We have given 2 milliamperes here. So I know a milliampere here. Bias point is straightforward. Okay. So let's come to this part here. So we put a ripple only. We put a ripple here. Bias. This is grounded. Both sides are grounded here. Here. Okay. Now what do we do with this? Well, if I have, no, what I can do is, as I said, I can take this particular block here, this and this block here, and I look down at this particular point. Note that what am I trying to do? I'm trying to transform this new thing into what I already know, my traditional circuit here. So what I'm going to do is I'm looking down from here and I'm saying, what does this appear as? Q3 with something attached here, what does this whole thing appear as? And I've done this over here. You can see that I can take this and write it as GMVS and R0. This appears as a current. Note that you take this, put this over here if you would like, and look at this one here and see that this is nothing. I can replace this by almost GMVS in parallel with R0. Look at this small signal here. VS connected here. At this point, what is the current that flows here? GMVS plus there's a current through R0. I've neglected that. Current through R0 is small here. So the net current at this particular node is GMVS. When I look at here, the net resistance that I see at this particular node is R0. Okay. So another way of saying it is, what you do is you build a Norton's equivalent at this point. Norton's equivalent at this node. But Norton's equivalent for what? For the circuit which is below that particular node. I'm only building Norton's equivalent for this part. Okay. Norton's equivalent for this part. So at this point, if you build Norton's equivalent, Norton's resistance is resistance looking down. When you look down, you remove the source. What do you see? R0. Fine. So that's the Norton resistance. Then what you want to find out is what is the Norton's current. So what you do is at this point you ground it and find out how much current flows here. So you can use this to find out that the current is practically GMVS. Okay. All right. So this whole thing becomes this then. Huh? Yeah, you can do that. Common base and all that. But common base, what do you want to do? See, the strategy, as I said, is what I'm trying to do is take this and go to something familiar, something that I already know. Okay, and something that I already know. And a general thing is when I have a block like this. So step by step, I would like to take this particular block and transform it into something simpler. I don't want to keep Q3 and all that. Transform it something simpler. So what I do is I take this block and I build a Norton's equivalent. See, what happens is if, a circuit can be broken into many blocks. Each block, if you take it and transform it into Norton's equivalent, what do you get? You get a current source and a resistor. So the whole block that you have simplifies into one current source and one resistor. Another block that you take is transform it into Norton's equivalent, becomes a current source and a resistor. So the circuit simplifies. Okay. So I'm left with this one. So I take this one here and I arrive at this one. Okay. GMVS here. Now what do I do? As I said, any of these analysis can be done in multiple ways. Okay. So this is one way of proceeding. Now note that I'm deliberately going and showing you the common mode. What do we do? Whatever is here, how do we build because of symmetry? Can you see that? This one single current source in R03 can now be written as 0.5 here, 0.5 here, 2R03, 2R03. Right? 0.5 and 0.5 will add up to 1. 2R03, 2R03 will give R03. Recall how did we arrive at the common mode circuit? We took whatever was, remember whatever was there below this particular part, we broke it into two parts here, 2RE and 2RE. Same thing I'm doing now. There's a current source here, but I'm building the symmetry. 0.5 GM here, 0.5 GM. Now what will I do? Cut it in the middle. Cut it in the middle here, because it's symmetrical, cut it here, and we're left with this. Okay, we are left with this. Now, what am I looking for? I'm looking for voltage at this node. What do I do at this node? At this node, if you're looking for it, build a Norton's equivalent. Build a Norton's equivalent. Do I know the Norton's resistance here? Resistance looking up, 6K. Resistance looking down into the collector. And not only that, to the emitter, I have all this attached here. That's a very large resistor. So Norton's resistance is simply 6K. So what it ends up is calculate the Norton's current here at this point. Norton's current here. Norton's current requires what? Make this ground. When this is ground now put this to ground. Now let's look at where the current is coming from. I want to know the Norton's current. Where is this current, Norton's current coming from? The source is here. Now if I look at it, what choice does this current have? It can either flow through 2R0 or it can flow into Q2. When I look into Q2, what do I see? When I look into the emitter of Q2, what do I see? 1 over GM. And it's a choice, this current has a choice between 2R03 and 1 over GM. Where will it flow? So this whole current that you see here will flow through Q2. And as it flows through Q2, where will it go? Into ground here. So IN is nothing but 0.5 GM3 VR here. The same current will be IN. And Norton's resistance, we've already said, is 6K. And therefore, you can calculate what is the output voltage. Final output voltage, we know GM3 VR, and you can calculate how much of it appears at this particular point. Okay. So as I said, the building of Norton's equivalent helps to simplify a lot of places. Okay. So wherever you are interested in finding out the voltage, build a Norton's equivalent. How much is the Norton's current here? Well, and then see the path of the current. Well, this is the current here. It has this path and this path. Where will it tend to go? Of course, a little bit flows here, but we'll always, as I said, we keep on making approximations at every step. At every step, we keep on simplifying. So this current flows through Q2. Of course, as it goes into the emitter of Q2, part of it can go into the base also, but the remaining part in the collector current is much higher than base current. So we say approximately the same current goes here and comes out here. Okay? Huh? 0.5 GM3 VR times 6K. You're right. So we'll end up with value of GM and we'll end up value of 6K. In this case, my differential amplifier is causing a problem. The ripple that you see here, you're right. When I work out my numbers, when I look at VR here, it's appearing in an amplified form. So there is an issue, problem here with this kind of biasing that you see here. Okay. Now this, the reason why this has appeared like this is because we put a ripple here, right, in 12 volt. But remember, the bias that you see here, where is this bias derived from? Where is it coming from? The bias will also be derived from the same supply. So what will actually happen is there's not only a ripple here, there will be a ripple at the bias also. In more practical cases, this is a simplified version. So there'll be a ripple here and there'll be a ripple here. And what will happen is the net base emitter voltage of, as far as the ripple is concerned, would be 0. And then you will find that it actually attenuates. Okay, here. Ripple voltages? No. See, the ripple is in the negative supply. And what I'm saying is this bias voltage that you see here in a practical circuit is also derived from the negative supply here. Okay, so the ripple will appear in the bias also. I'm talking about a practical case. Okay, will appear also. So it appears as if yes, it is getting amplified in this particular case. It may not get amplified in that much in the other case. All right. Question number 8 is determine the differential and common mode gain of the circuit shown below. All right. So here note that we don't have a ideal current source. We have a current source, and when I put something like this here, 100K, what it says is the current source has a resistance also 100K associated with it here. Okay. Note that what would happen is so the current source is ideal, So what would happen is, as far as bias point analysis, if I put 0 here, this would be minus 0.7. And so the effective voltage here is 11.3 divided by 100K. That's how much? 11.3 divided by 100K, 0.1 milliampere here. So it's not entirely negligible compared to this. Okay. So you'll have to sort of add up these two and then say how much current flows here and how much current flows here. Okay. It's about 10% of that. Maybe I should have chosen here 1000K. That would have, at least bias point would have been determined by 1 milliampere here. All right. Anyway, I'm sure you can calculate what the bias points are. Okay. Now, when you calculate the bias point also, so we know the current is going to divide equally and all that. And so we have to find differential and common mode. So differential mode analysis, as usual, we put 0.5 VID minus 0.5 VID here. And the resistor that you see here, 20K, we break it up into 10K, because note that our differential mode and common mode are all based on trying to build symmetry. Okay, so 20K, we build 10K and 10K here. We know that this point will be ground. And 0.5 VID, what will it try to do? It will try to make this voltage positive or negative? 0.5 VID here will try to make this voltage. What is there's a phase shift of 180. So it will try to make this voltage negative. And minus 0.5 VID, there's again a phase shift of this. It will try to make it positive. Both equal amounts. Negative here and positive here, equal amounts. So what would happen at the center? 0. So this circuit will become a small signal ground here. This is also a small signal ground here. So the whole circuit reduces to 10K, 10K, and now it's a simple common emitter amplifier you can easily solve. Okay. So if the circuit is not symmetrical, try to see how can I make symmetrical by breaking it and this and that. Okay. Common mode is even simpler. Common mode, I apply VIC here and VIC here. And note that by symmetry, the voltage here and the voltage here are going to be the same. Whatever voltage appears here and here are the same, and therefore no current is flowing here. Just remove it. Common mode part, the resistor gets removed. And then this resistor is 100K. Note that current source is ideal. So this is only 100K. And now what you do is you have a normal differential pair with a resistor here, and resistor here. So normal, same GM, this is RC and RE is 100K, and solve it. Okay. All right. This is a normal differential pair with current mirror load, straightforward application of formulas. GM, R02, R04, calculate ADM. And as I said, we can't calculate ACM. We said ACM calculation is far more difficult, and we've left that here. All right, so this is straightforward. Question number 10. For the two-stage amplifier shown in figure 10, determine the net differential gain. Okay, take a look at it. Note 2 milliamperes here. All transistors, unless otherwise, if nothing is said, all transistors are identical. Okay. So 2 milliamperes going here. I've not written this thing here. Note that when I draw like this here, it means all the bases are connected together, right? All bases are connected together to V bias. So how much is the current in this transistor? 1, 1, and also here 1. Okay, so current here is also 1. Everywhere is 1. 2 milliamperes, 1 flows here and 1 flows here, obviously divides. And now this transistor is identical, same base emitter voltage, 1 flows here also. Okay, so bias analysis is okay. Now gain of this transistor would be, note that I'm taking the output from here. So first of all, I calculate what is V0 at this point divided by VID. Divided by VID, that's ADM1. Now once V01 comes here, it gets further amplified and appears over here, that's AV2. Okay, overall gain. Overall gain would be gain of the first stage multiplied by the gain of the second stage. Now, gain of the first stage here. Note that if I look at the gain of the first stage, whenever you have multi-stage amplifiers, you have to worry about the second stage will always contribute as the load resistance of the first stage. So when I look from here at this point. When I look from here towards the right, I see base and I see this will be ground here. So I see R pi 5. And R pi 5, and note that the biasing of this stage is exactly the same as biasing of this stage here. R pi 5, and what is this stage here, Q4? Is base and collector are shorted together. So Q4 is nothing but if I look at between here, this node and ground, I see 1 over GM4. Under small signal condition, note that this is like a normal differential pair with a load here between here and here. And base and collector are shorted together, both of them. So each one of them acts as, instead of RC, under small signal condition, what do I have? 1 over GM4. Under small signal condition. So this will act as 1 over GM4. And then this one contributes what? R pi 5. R pi 5 is much, much larger than this, so it doesn't bother. As far as the first stage is concerned, it doesn't affect me. Okay? And the gain will be 0.5 GM, GM1 or GM2 is the same, 0.5 GM RC. RC is what? 1 over GM4. That's the first stage. No, so there is a mistake in this problem. So what it is that this is connected here. This is also connected here. The two bases are not connected. They're two independent. That's what was intended. This base is connected here, right? And the base of this is also connected here. And the two of them are separate. Q3 and Q4 are separate. They're not connected to each other. Okay? Let me modify it. Okay? What was intended. Okay? So let's modify this. All right. So this circuit is supposed to be and what happens is I need more space here. The two bases are also not connected, so I need more space here. All right. So this is how it looks here now. What? Here. Okay. Now there's a mistake here. All right. That's better. Okay. The two are separate. We are not building a current mirror or something like that. Let me just remove this also. Okay. Now look at this. That's how it is. Why? Current in Q3 and Q4 is decided by here. Q1 and Q2 are identical. Bias point. This is 0, this is 0. So the same current 2 milliamperes, 1 milliampere flows here and 1 milliampere flows here. Q3 and Q4 are also identical. They're all connected in the same manner here. Fully symmetrical circuit. It's a fully symmetrical circuit here. Okay? Yes. Saturation where? Q3 and Q4 are this thing, right? Q3 and Q4 are with base and collector, they will always be in active mode. They will always be in active mode. If I have 12 volt here, then the drop from here to here would be 0.7. So I have 11.3 here and 11.3 here. But I have what you guys can see is 11.3 here and 12 here. So there's also 0.7. So there's no problem with biasing or anything. Same current, 2 milliamperes flows here, half flows here and half flows here. There was a mistake here that the two are connected together. That's not true. Okay? That causes is coupling the left half to the right half also. We don't want that. So that's a variation if you want to analyze it and see what happens. Okay? It's connecting the two halves together. That's the problem. Okay? That's the problem. So this is what was intended, the circuit here. That's why we were saying that between here and here, I have simply 1 over GM4. Between this node and 1 over GM4. Between here and here, 1 over GM3. So it's a perfectly symmetrical circuit, and that's why we can keep the same result here. 0.5 GM2 RC, which is 1 over GM4. Okay, and since GM3 and GM4 are identical, GM1 and GM2, all GMs are the same, and so they cancel each other. The gain of the first stage is simply 0.5. Okay, the next stage, the gain of the next stage. So when I look at the next stage here, it goes to the base of this Q5, and it's a common emitter amplifier. It goes to the Q5, and we are asking for voltage at this particular node here. So this Q6, note that there's nothing applied, no voltage is applied to Q6 here. So Q6 is nothing but bias is under small signal condition. This would be small signal ground. So when I look down, this is ground, and I look down and I see into the collector of Q6, and what I see is R06. So as I said, it's a common emitter amplifier. The net gain of this amplifier is GM5, and whatever is the net resistance at this node. Resistance looking up and resistance looking down. When I look up, I see again into the collector, R05. When I look down, I see again into the collector of Q6, R06. So that's the gain of the second stage. So overall gain then becomes 0.5 times GM5 R05 parallel R06. And of course, after that, you know, bias point is already done, so one can calculate. Okay. All right. The last one, two differential pairs are there. You know, when you get a circuit, when a circuit like this is given, you'll be given at least 15-20 minutes are allocated to solve a circuit like that. Okay, maybe 2-3 minutes you should look at it. What is it? Before jumping and saying, what is this particular circuit? All right. And if you look at it, maybe it's drawn in a funny manner. It could have been drawn in a, you must have seen, you know, a lot of JE problems you would have seen that you have these resistors. They're all drawn deliberately in a complicated manner. And if you redraw it in a nice manner, it becomes simple. Okay. So maybe this is also drawn in a slightly complicated manner, but all that if you look at it, if I pause and look at it, okay. All right. Let me break it up like this. There's an inner differential pair and there's an outer differential pair. The inner one, let me focus on inner one. Inner one is Q1, Q2, 2 milliamperes, 1.5K, 1.5K, and the output goes into the base of Q3, the output goes into base of Q4, right? That's the inner differential pair. And that looks straightforward, inner differential pair. Except that when I'm solving it, note that, and when I'm solving it, the second stage will act as the load of the first stage here. So when I look right, what do I see? When I look right, I'm looking into the base of Q4. And what is connected to the, here, Q4, the emitter? I'm doing differential mode analysis. So what would happen is Q4, this point here would also be ground. Okay. So I'm looking into the base of Q4. And also note that when I look into the base of Q4, I basically will find R pi 4. And R pi 4, so to know how much is R pi 4, I have to look at the outer differential pair. The outer differential pair looks like this. It's a differential pair, PNP differential pair with an NPN current mirror load. Note that it's a current mirror load. And is biased at 0.2. So effectively, 0.1 milliamperes will flow here. 0.1 milliamperes will flow here. And you can calculate, how much is R pi 4. Okay. And I think if you do the calculation of R pi 4, probably it will come out to be significantly larger than 1.5K. If it doesn't, what you can do is under small signal condition, if this is still comparable, you can take a parallel combination of 1.5K and R pi 4. Okay. So that's what the differential pair under small signal condition would look like. Effective RC for small signal calculation would be 1.5K in parallel with R pi 3 and will be parallel in R pi 4. Okay. Note also further that I've biased it by current source, ideal current source. Ideal current source, which means common mode gains are all 0. You don't have to bother about common mode gain. All right. So this is now the differential R pi here will come in parallel with this. So you can easily now analyze this and find out how much is the voltage here and how much is the voltage. That's fine. How much will be the voltage at this particular point? There will be a bias voltage. Can we calculate the bias voltage? 1 milliampere here will flow here, and we can calculate what is the bias voltage and what is the bias voltage here. We can also calculate what is the, because of this V in, what is the differential voltage here? What is the differential voltage here? Both of these things we can calculate. Common mode is 0. What is the net differential input voltage? V in. So you'll get some part here and some part here. Now what you do is you go ahead and put these two values here at this particular point and this particular point. Can you see that this particular point will have, let's say, a negative value, let's say, and this particular point will have positive value, because V in will contribute a voltage here, let's say positive, and a voltage here which is negative. How much voltage here? Well, you know the gain, differential mode gain. All right, so you know these values here. Along with that, there is a bias voltage here, and bias voltage here and bias voltage here are the same. So bias voltage here and bias voltage are the same, which means that the bias voltages are common mode signals. So you don't have to bother about common mode, because common mode gain is 0. It's an ideal this thing here. So you can calculate now for this current mirror, what is the net differential input voltage for this current mirror. Net differential input voltage, which is what? V01 minus V02. And now this is a current mirror. This is a differential pair with current mirror load. So if eventually what happens is this then. ADM1 is 0.5 GM RC parallel RL. RL is R pi 3, R pi 4, VT by this. So it comes out to be 26K. At least, I mean, it's more than 10 times higher. So first order approximation, if something is 10 times higher, you are free to neglect it, okay, in the exam. So 26K, 10 times higher, you ignore it. So you have only 1.5K, 1.5K, you know ADM1. The two outputs of the first stage serve as input to the second differential pair. And the gain of the second differential pair is a current mirror load. We've already calculated gain of a current mirror load is GM4. GM4 or GM3 is the same. R04 parallel R06. And the overall gain, basically you'll find V in into ADM1 into ADM2. Because the second stage does not load the first stage, so the gain will become simply that. Okay. So basically one differential pair cascaded with another differential pair. All right. So that's what problem number 11 is. All right. So let's stop here then.